So in the previous video, were able to already derive the standard form of the equation of the ellipse with center at 0, 0 and is oriented horizontally. There are actually four standard forms to take note of, just like the parabola. So for the standard form of the ellipse, we have to consider two things. First, where is the center of the ellipse located? And second, what is the orientation of the ellipse that we're talking about? Is the center at 0, 0 or is it at HK? And is the orientation horizontal or vertical? If the orientation of the ellipse is horizontal and it's at 0, 0, the center of it, that's what we have derived in the previous video, and that is x squared over e squared plus y squared over b squared equals 1. Now, this is too small. Let's make it big. Alright, there we go. So for horizontal, with center at 0, 0, that's what we derived a while ago. That's x squared over a squared plus y squared over b squared equals 1. Now, we were also able to show, and we can also figure that a is greater than c. And if a is greater than c, a squared will be greater than c squared. And since b squared is equal to b squared minus c squared, if we're going to do transposition here, because as you can see, c squared is not in the equation in standard form, c squared is equal to a squared minus b squared, which implies that a squared is greater than b squared. And this is important because in the standard form, the bigger denominator is always a squared. And wherever a squared is, it dictates the orientation of the ellipse. So if the orientation is horizontal, then a squared, the bigger denominator, should be below the denominator, below the x term. So in HK, if it's horizontal, it becomes x minus a squared over a squared plus y minus a squared over b squared equals 1. If the orientation is vertical, let's write that more vertical. If that is the case, then it should be below the y term, the a squared, the bigger denominator. So for with center 0, 0, and vertical orientation, the standard form becomes x squared over b squared plus y squared over a squared equals 1. And for HK, it becomes x minus a squared over b squared plus y minus b squared over e squared equals 1. So these are the four standard forms that we would have to take note of. And with these standard forms, now we can take note what are the parts of the ellipse that we have to look for. First is the one that is most obvious, the center, which is either at 0, 0 or at HK. After looking at the center, we usually take a look at where a squared is to determine whether the ellipse is horizontal or vertically oriented, because that's important when we check the coordinates for the other parts. Now, so that's the next step, whether we check if it's horizontal or vertical. After that, we then check the values of a squared, b squared, and c squared. A squared and b squared are part or are seen in the equation. C squared is computed using this. It's a squared minus b squared, not plus. That's Pythagorean theorem. We get a squared, b squared, and c squared because a, b, and c are important values that we get to find the parts of our ellipse. For a, what we get here are these 2 points here, b sub 1 and b sub 2, which we call the vertex. Plural, vertices. Vertices. So there you go. So as we can see, the distance between the center to the vertex is a. Center to the other vertex is also a. There you go. So a is related to our vertices. Now, the other name that we can call this, since this is a line segment, I don't know if it is obvious, but here it's not that obvious. You can just highlight this. So this line segment here that contains the center, contains the center and the vertices is what we call the major axis. So the major axis, I shorted it with capital and capital A, is also related to A because the length of the major axis is equal to 2A. And this also tells us that the vertices can also be called the endpoints of the major axis, which is I usually shorten as capital M, capital A. Now, for B, what we get here is this one here. From the center to this point here, that's B units, and from this one here, that's also D units. So these 2 points here, I usually call them as CV1, CV2. These are what we call our co-vertices. And so the distance from the center to a co-vertex is B, regardless if it's at 0 or at H8. And this line segment, I'm going to highlight it in brown. This, the line segment that contains the co-vertices of the center perpendicular to the major axis is what we call the minor axis, which I shorten as small letter m, capital letter A. Therefore, this tells us that if the distance between the center to a co-vertex is B, and the other co-vertex is also B, therefore the length of the minor axis would be B. Further, the co-vertices can also be called the endpoints of the minor axis, which is sometimes shortened as capital E, small m, capital A. So the endpoints of the minor axis. For C, this is only on the coordinates of the foci. But take note that whether it's the foci, the vertices, or the co-vertices, they should have the same midpoint, which is the center of the ellipse. So now, so far we have these points, the center, the vertices, the co-vertices, and the foci. The next thing that we would now have to look for would be the endpoints of the latus vector. In an ellipse, you don't just have one. You actually have two. And if the plural of latus rectum becomes latera recta. So you have two latera recta in our ellipse. To find the coordinates of the endpoints of the latus of each latus rectum, that would be b squared over a. This is also one of the other reasons why we usually get these values, because we do them. So the length from the focus, from one focus to the TLR, that's b squared over a. And this is also b squared over a. Meaning, it's b squared over a that we add or subtract to the coordinates of the focus depending on the orientation of the latus rectum. As we can see here, this ellipse is horizontally oriented, and both latera recta are vertical. Therefore, if the ellipse is vertical, then the its latera recta would be horizontal. So, how can we easily remember that? The minor axis. The major axis is the one that tells the orientation of the ellipse. The major axis is the same as the orientation of the ellipse. Therefore, the minor axis is perpendicular to that. So if the ellipse is horizontal, the minor axis is vertical. And the lateral recta is parallel to the minor axis. They have the same orientation. So if the ellipse is horizontal, perpendicular to that, so the minor axis and the lateral recta, all three of them would be vertical. If the ellipse is again horizontal. So it depends on the orientation of the ellipse on which coordinate we add b squared over a from the coordinates of the focus. This will then tell us that the length of the latus rectum would be 2b squared over a, because that's 1b squared over a and another b squared over a. So these are the parts that we usually get when we solve for the parts of that ellipse. So once again, we have these slides that would summarize those. This is the first slide where we have the case which center at 0, 0. This is a horizontal or horizontally oriented ellipse. This is a vertically oriented ellipse. Then we would have the next if the center is at HK. These are the parts for the horizontally oriented ellipse with center at HK. This one is the vertically oriented ellipse with center at HK. So let's now try, given certain equations, let's now determine the parts of the ellipse and then let's try also to sketch its plan. So let's start with number 1 and go back to here. But we have more space to write. So 1a tells us that we have to find the parts of x squared a squared plus y squared over b squared equals 1. Now, not x squared over y squared. Let's change that. The actual equation is x squared over 169 plus y squared over 144 equals 1. The first question now is, what is the center? As we can see, there is no HK in the x and y term, so therefore it's safe to say that the center is at 0, 0. With that, we now determine what is the largest denominator. And it's 169, and it's below x squared. So therefore, this ellipse is horizontally oriented. With that in mind, we now have to get what is a squared, what is b squared, and the value of c squared as well, because it will help us in the other parts. So the largest denominator is always a squared, which is equal to 169. B squared is automatically the other one, 144. And c squared is a squared minus b squared. So that's 169 minus 144, which is equal to 25. So therefore, 8 is equal to 13, b is equal to 12, c is equal to 5. And we get the square roots, which would be important now to look for our parts. Now, since we are also told that it's horizontal, it might be helpful if we are going to have a very rough sketch of our ellipse. This is our center at 0, 0. So first, A. If we recall, A is related to the vertices. But the vertices is expected to be here and here. And the distance between the center to the vertex is A. Center to the vertex would also be A. Now, since our center is at 0, 0, and since it's horizontal, a horizontal ellipse, the vertices will be we're going to move from the center to the right and then to the left to get to the vertices. In this case, 13 units to the right and 13 units to the left of 0, 0. Therefore, the coordinates of your vertices, this would then be at 13, 0, 13 units to the right of 0, 0, and this one would be negative 13, 0, 13 units to the left of 0, 0. So now we have our vertices, which can also be written as plus minus 13, 0, since that's what we have, 13, 0, and negative 13, 0. Next, now we get the co-vertices. So, if the vertices is moving up, before we go to the co-vertices, I forgot, let's now get the major axis. The length of the major axis is simply 2a, which is 2 times 13, which is equal to 26 units. Now we go to the co-vertices or the co-vertices, and later on the minor axis. If the the ellipse is horizontal, then the minor axis should be perpendicular to it. So in this case, here will be our first co-vertex and our second co-vertex, since our minor axis is expected to be vertical, perpendicular to our horizontal major axis and our horizontal ellipse. So therefore, we go up and down. How many units? That's b units up from the center and then b units down from the center. In this case, b is 12. So therefore, from 0, 0, we move 12 units upward. Hence, this will have now a coordinate, or it will have coordinates of 0, 12. And down below, if we move 12 units down from 0, 0, it becomes 0, negative 12. Or this can be written as 0, positive, negative 12. Now, for C, this is the foci. So from the center to this point, that small letter C, which is 5. So this will be the first foci, and from the center to the other, this will be the second foci. And that's also C equals 5. With that in mind, so that C units to the right of the foci, and we set to the right because as you have seen a while ago, the foci is also on the major axis. So if the vertices are moving from left to right, so does left to right of the center, so does the foci. So from here, so from 0, 0 to 5, so one of the foci would be 5, 0, and to the left of 0, 0, 5 units, that's negative 5. 0, or that would be plus minus 5, 0. So now that we have our focus, we can now get the endpoints of our latera recta. This is one latera recta here, and this is the other. Oops, this is the other. Just again, here you Here you go. This is our 1. Oops. This is our 1, 2, 3, and 4 endpoints of the lattice recta. Now, as we can see, I'm going to highlight it in green, so let's put it here. We can notice that the highlighted latera recta in red are vertical. That means it should have the same abscissa as our foci, since it's literally aligned. So we're going to have 5 comma something, 5 comma something, and 5 comma something, 5 comma something. Because it has the same abscissa from the two foci. And we know that from one focus to the endpoint, that's b squared over a, which in this case, b squared over a is equal to 144 over 13. That means from 5, 0, we go 144 over 13 units up. Because that's from 0, so you just keep that. And then we go down also 144 over 13 units. So therefore, we go down. That's negative 144 over 13. And this happens also here on the other latus rectum. This becomes plus 144 over 13. This becomes negative 144 over 13. And because of this, we can say, or we can write this as positive negative 5, positive negative 144 over 13. So now our parts are complete. We have your center, your vertices, your co-vertices, your co-vertices, your foci, your endpoints of the latus rectum. The lengths are usually asked, but they are not considered as parts. Which, by the way, if we want to find the length of each of our latus rectum, that's 2 e squared over a. So that's 2 times 144 over 13, which is equal to 288 over 13 units. We forgot the length of the minor axis here. The length of the minor axis would be 24 units. Because it's 2 times the value of t. So lastly, if we are to sketch the graph, this will be quite long because we have here let's take minutes. Let's go down a bit. Let's make this long partition. Okay. So first, to graph, usually we would need our vertices and co-vertices. The foci can also be included in the ELRs if it's convenient. Here, the ELRs, they're not convenient because they are not integers. So we rely on our vertices and co-vertices. So for our vertices, it's 13. So hopefully we can reach 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Here it is the first vertex. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Here is the other vertex. For the co-vertices, it's 12. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't reach 10, 11, and 12. So we would need to extend our there we go. While down below, let's see if it will reach. It is not, so let's extend already. There you go. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the second co-vertex. Other co-vertex is here. So since it's a bit big and it cannot fit in our screen, let's zoom out a bit. There you go. So although it will look like it's a circle, but the foci is 1, 2, 3, 4, 5 here. It's actually the second foci. Let's just zoom back to normal. So actually here is our foci at 1, 2, 3, 4, 5 here. This is the second foci. This is the first foci. And you can interchange that actually. So we're going to make this look like an ellipse. So somehow it should look like a circle. It should look like whenever I draw it. There we go. It should go somehow down. And from here, it should somehow go like that. It doesn't look like it's perfect. So this here is the sketch. So here, this is the sketch, and these are the parts. There you go. These are the parts of the equation x squared plus 169 over y squared over 144 equals 1. Now, what if the given is not in standard form? It's in general form. Alright, so let's take a look at C instead. So at C, we have 4x squared plus y squared plus 8x minus 4y minus 8 equals 0. So from here, we can see that it's a general form. So how do we now write this? Or how do we now get this to standard form? Because it's in the standard form where we get the parts. First, write together the ones with the same variables and those without transposing to the right side. So therefore, we're going to have 4x squared plus 2x plus y squared minus 4y equals positive 8. So we see we have first degree terms here, which can imply that we're going to have x minus h and y minus a respectively, because if not, it will just simply be x squared and y squared. So to do completing the square here, because we expect to have a square root binomial, the coefficients of the squared terms must be 1. This is 1, but this is not 1. So 4 should be factored out from these two terms. We would have 4 times 4x squared divided by 4 is x squared. 8x divided by 4 is 2x. While y squared minus 4y remains the same and 8 also remains the same. Now we can complete the square. So this becomes a square of a binomial. So here, we're going to have that's 2x divided by 2x then squared. It becomes 1 squared, which is equal to 1. Here, we're going to divide negative 4y by 2y then square it. This becomes negative 2 squared, which is equal to 4. Hence, what we add here and here would be 4 times x squared is 2x plus 1. That's what we add here. Then the other one, that's y squared minus 4y plus 4. Now, since we added 4 here, we should also add 4 here. Now, a warning. If you're going to add 1 here because we added 1 here, that's wrong. Apart from adding 1, you should also multiply it to 4. So in doing so, we're going to have 1 times 4, and that's 4. So that's what we add here. So that's 8 plus 4 plus 4. Now you can write this and this as squares of binomials. So this becomes 4 times x plus 1 squared plus this becomes y minus 2 squared is equal to 8 plus 4 plus 4, that is 16. So now in standard form it's 1, so therefore we divide both sides of the equation by 16. This becomes 1. 4 divided by 16. 4 divided by 16, that's 1/4, so we're going to have x plus 1 squared over 4. Plus, this becomes 1 over 16, so that's y minus 2 squared over 16 equals 1. And now that we have the standard form, we can now then check the parts. So, first, as we can see, we actually have a center. We might need to figure this is here, so I'll write this one here. Do not mind this first. So first, we have here our center, that's the negative 1, 2. And seeing that 16 is under y, this is a vertically oriented ellipse, which is different from the first one because that's horizontal. So now, before we do anything else, let's look for a squared, b squared, and c squared. A squared, again, is the biggest denominator, so that's 16. B squared is 4. C squared would be a squared minus b squared. That's 16 minus 4, which is equal to 12. So therefore, A would be equal to 4, B would be equal to 2, and C would be equal to 2 square root of 3. So now we have, let's try to graph that. So we have a negative 1, 2. Here is the center. Now, from there, we can now try to count how many. We will now try to count not how many, but where would be your parts of the ellipse. Now, for A, which concerns the vertex, since this is vertical, this time, the major axis is vertical. Hence, to get to the vertices, we go up and down. In this case, we go up 4, 1, 2, it doesn't fit, 3, 4, wait a moment, let's fix this here. erase this. So let's fix that. So -1, 2. That's our center. So we go up for 1, 2, 3, 4. Here is the first vertex. If we go down for 1, 2, 3, 4, here is the second vertex. 1, 2, oops, sorry, not here. Put this out. 1, 2, 3, 4. Here you go. There you go. So this is A units, which is equal to 4 from the center to this one. And as you can see, they're vertically aligned, so the vertices would have the same abscissa as the center, which is -1 for one vertex and -1 for the other vertex. In this case, from 2, we added 4. So that's 1, 2, 3, 4. 3, 4, 5, 6. It's 2 plus 4. So this is now a -1, 6. And the other one, we subtract 4. So that's 1, 2, 3, 4. And that will be 2 minus 4, which is negative. Cannot write plus minus here because we don't have the same sum and one positive, one negative of the same absolute value number. But we can know from here that the endpoint of the, not endpoint, but the length of the major axis is 2 times 4, which is equal to 8 units. From now the vertex, we now go to our whole vertices, and that is P. So from here, since we went up and down for the vertices, we now go left and right for the co-vertices. We go 1, 2 to the right, and then 1, 2 here to the left. And from the center to this, that B is 2 units. From here to here, that's also 2 units. Therefore, what moved, or what's the same with the co-vertices and the center would be your ordinate. And that ordinate is actually 2. So now we just need to have an abscissa. So this is B is 2, so that's 1, 2, which is -1 plus 2. Be 1. So the other one would be here 1, 2. That's -2, -3, which is actually -1 minus 2. Because for again, this is -1 plus 1. This one is -1. That's that is -1 plus 2. The -1 minus 2. So this becomes -2, -2. Becomes -3, 2. From here, we can also get the endpoint of the minor axis, not endpoint, the length rather of the minor axis, which is 2b. That's 2 times 2, which is equal to 4 units. Finally, for C, although it's a bit complicated to look for where C is, 2 square root is approximately between 3 to 4 units. So with that, we just need to count approximately 3 to 4. Past 3. So from the center, that's 1, 2, 3. Then point something. So the focus might be somewhere here. And from this down below, that's 1, 2, 3. So it might be something here. F sub 2, F sub 1. And from the center to the focus, that would be C, which is 2 square root of 3. Same here. This would be 2 square root of 3 units. With that in mind, therefore, what we add, because it's going up, or subtract going down to the coordinate of our what do you call this? The ordinate of our center to get the coordinates of our focus, of our foci. So for the foci, that's -1. Then from 2, we go up 2 square root of 3 units. So that's 2 plus 2 square root of 3. And when the point went down to the other focus, that's -1, then 2 minus 2 square root of 3. Or we can write this as -1, 2 plus or minus 2 square root of 3. That's for the for the foci, rather. Now, we now go to the endpoints of our latus rectum. As you can see from our foci, we already have an irrational number here. So all we can do is add or subtract according to our analysis. If this is where the first focus would be, somewhere here, and the other focus would be here, somewhere here, then that means since it's vertically aligned, not vertically, horizontally aligned, our ELRs are horizontally aligned as such, then they're going to have, the ELRs will have the same coordinates as our foci. So therefore, it will become blank, then 2 plus 2 square root of 3, then another blank which says 2 minus 2 square root of 3. So the other ELRs would follow suit. That's 2 minus 2 square root of 3. Here, that's 2 minus 2 square root of 3. So now, we need to find our b squared over a, which is this and this. So b squared over a would be equal to 4 over 4, which is equal to 1. So that means from -1, we need to add or subtract. So if we're going to add 1 to -1, that becomes 0. Going to subtract 1 from -1, that becomes -2. And although the graph is a bit difficult to sketch, we have our vertices and co-vertices to help us, because it's kind of difficult to graph the focus and the ELRs. So if we're going to graph this, let's just have this here, and 1 would be here. Here we go. So for our graph, our vertices are -1, 1, 2, 3, 4, 5, 6. This is the first vertex. The center is at -1, 2. Here, then the second vertex would be at -1, -2. Alright, there you go. So for this is the second vertex. So for our co-vertices, we have at 1, 2. And then we also have at -3, 2. All we need to do now is sketch its rough graph. Still doesn't get the ellipse. Apologies. Ellipse, but that's what the sketch of the graph of this general form equation from here to here. This time, what if we have the other way around? We're given some parts or some conditions, we now have to find the equation of the ellipse in general form. So let's take a look at A. The center is at the origin, so that's 0, 0. One vertex is at 0, -6, and the one co-vertex is at 4, 0. So if we're going to analyze that, let's draw a small partition here. So the lower part is more important. The origin is this, 0, 0. So 0, 0. Then, one vertex at 0, -6. 1, 2, 3, 4, 5, 6. 0, Since one co-vertex is 1, 2, 3, 4, 0. So what would now be the equation of this hyperbola? Now, we are given with the center, so we can use that and with the distance from the center to other points to find the parts. In this specific case, this is center and this is vertex, so therefore this should be A. That's 1, 2, 3, 4, 5, 6. If A is equal to 6, therefore we can use that later in our general form. Now from center to co-vertex, that is B. And if this B is equal, that's 1, 2, 3, 4. So therefore, if we are to write this now already, since we have already A and B, we just need to square them, so that's 96, and square this, which is 16. So now, before we write, we have to determine whether it's horizontal or vertical. But as you can see, from center to one vertex, we went down. That means this alignment should be vertical. Hence, A squared should be below Y squared. Since the center is 0, 0, we can then write this as x squared over 16 is equal to y squared, not equals 1, plus y squared over 36 equals 1. So now from there, we get the LCD so that we can better take a look at the pictures. So now, just to find our LCD, I guess this is 144, but just to show, 16 is 2 times 2 times 2 times 2, 36 is 2 times 2 times 2 times 2. So once we get these LCDs, that's 2 times 2, that's LCDs GCF, times 2 by 2 times 2 by 2, this actually solves to 144. Because it's 9 times 4, 36 times 4 is 140. So with this in mind, we can multiply both sides of the equation by 144. Therefore, this will become 144 divided by 16. That gives us 9. That's 9x squared plus 144 divided by 36 is 4 plus 4y squared. Sorry, 4y squared is equal to 144. So to make it general form, that should be 9x squared plus 4y squared minus 144 equals 0. Now, before we go to the others, since they have centers, let's go to a problem that is not or does not have a center. Let's look at letter D. The foci is at 0, negative 8, and 0, 8. The length of the major axis is 34. What information can we get from here? From this, the length is equal to 34, and that's 2a. Divided by 2, a would be equal to 17. The question is, how do we get to it? Or not how, but how will this now help us in finding the equation? So now that we have A, if we know the center, then we can easily count. The thing is, we don't have the center here, but we do have the two foci. And remember, the midpoints of the vertices, co-vertices, and the foci should be the same, which is the center. So if we get the midpoint of our two foci, that's 0 plus 0 divided by 2, 0. Negative 8 is divided by 2, 0. So the center is at 0, 0. Therefore, it will be a lot easier for us. Further, as we can see from here that our foci are different when it comes to ordinates. Hence, therefore, we can say that this is a vertical ellipse, which the foci are aligned vertically. From there, we can also compute C, because that's the length from the center to the foci, which would be 8 units. Now, to have the previous PD, first we need to get this as a squared. Becomes 289, while c squared will be equal to 64 because that's 8 squared. Let's remove that because we need b squared. So if c squared would like to be it would be 64, then b squared should be, so 289 minus 64 should be 225. We get the square root of this is 17, this is 50, and this is 8. So with that defined, now we can find the equation of the ellipse. Although we showed this to find, if just in case rather, we need to look for the parts. But for the equation, all I need is a squared with b squared. Since the center is at 0, 0, this becomes x squared over, since this is vertical, so x squared should have a denominator of b squared. Plus y squared over a squared equals 1. Now, to make this in general form, we have to multiply both sides of the equation by the LCD. Since the two numbers are relatively prime, meaning they don't have a common factor, we just multiply the product of 225 and 289, which is 65,025. Therefore, this would become 289x squared plus 225y squared is equal to 65,025. Then we transpose. So therefore we're going to have 289x squared plus 225y squared minus 65,025 equals 0. This is the general form of the equation of this ellipse.